We're going to start on Newton's law of universal gravitation. In order for us to do this, you need to download these three documents: the Newton's law of universal gravitation notes, the planetary data, and the universal gravitation practice problems. We're going to be using these two for the notes and information, and this will be a set of practice problems that you do after we get done taking the notes. All of these can be loaded into Notability. And this one you need to have opened up. Again, you can either print this off or use it in Notability, either one. You will not be turning this in, but you'll need to take the notes on it in order to be able to solve the problem and be ready for quizzes and tests that are coming up. So the notes packet will look something like this. There'll be notes and blank spaces and large areas where we take notes on. The planetary data table will look something like this. It has all the information about the sun and the planets that orbit the sun. And then, of course, the practice problem sheet will look like this: 2 pages of practice problems that you'll do after we get done with the notes. So let's go ahead and get started. In the historical context about Newton's law of universal gravitation, the reason it's called universal gravitation because, again, during this time of Newton, he lived in about the mid-1600s, people still thought that the laws that governed how things behave on Earth were very different than how things were governed in the heavens. Universal simply means it's something that happens on the Earth and in the heavens. It happens to the planets, the stars, everything in the universe. So historical context. Almost everyone has heard the tale of Newton's apple. Sir Isaac Newton sat under the apple tree, and the story goes that an apple fell on his head. At least this is the story. And this led him to develop what's called the law of universal gravitation. There is some truth to this story. Whether an apple fell on Newton's head or not is somewhat debatable. It probably did not. But there is some truth. In the archives of London's Royal Society, there was a manuscript by William Stukeley, who knew Newton and interviewed him during the last year or 2 years of his life. He wrote a biography entitled The Memoirs of Sir Isaac Newton's Life. Stukeley described how Newton explained the apple story to him. So if you read this information, it kind of explains, this is Newton talking to Stukeley and Newton explaining how this apple tree was famous for developing the law of universal gravitation. Over to the right, there's a picture of this apple tree on Woolsthorpe Manor where Newton lived as he was developing this law of universal gravitation. Now, an interesting thing, in 1665, the Great Plague of London caused Trinity College to be closed. This is where Newton went to college, and he had just earned his undergraduate degree. But the plague started plaguing London and England, and he went back home to his home in Woolsthorpe. And he spent this year in what we now know, and what we're familiar with, in social isolation, so that he would not contract the plague. And during this time, during this year, 1665, was the most amazing year in Newton's, at least, scientific career. And he studied physics, and he contemplated why that apple fell to the ground. So let's take a look at some of the information in Newton's law of universal gravitation. Newton reasoned something like this: a force must be acting on the apple to pull it to the ground, straight down to the ground. Never went sideways or at an angle, always straight to the ground. Newton theorized that the force pulls on the apple. If the force pulls an apple to the ground, it must pull all other things to the ground. If it's then an apple, there was a large rock, the force on the rock would be larger than what the force on the apple was. If the object was a small stone, which is smaller than an apple, then that force would be smaller than the force on the apple. So the mass of the object affected the force in what we know as a direct relationship. If the mass went up, the force went up. The mass doubled, the force doubled. Mass tripled, the force tripled. If the mass decreased by half, the force decreased by half. That's a direct relationship. But Newton went further on. Well, the thing that's pulling on this apple is the Earth. So Newton theorized that the apple, or the object that was on the Earth, caused the force to increase. Well, then the Earth also had mass, so the mass of the Earth also affected the force on the object. Also, Newton knew that the further something was away from the Earth, the less the force of gravity there was on it. So also the distance between the two objects affected the force. Now we'll write this in some mathematical type of relationships. We used proportionalities before. Remember, we use the proportionality sign or the proportionality equation because they're not equal to each other. So for example, the force of gravity, we're going to use force of gravity. This is a capital G instead of a lowercase g because it's based on the masses of the object, not on their acceleration. The force of gravity is proportional to the mass of one object. We have two objects, like for example, the Earth and like an apple on the Earth. This is the apple. And there, the force of gravity is applied to these two objects. We have two objects. Say this is the mass 1, this is mass 2. So the force of gravity is proportional to mass 1. If this mass gets larger, like an apple or a large rock or a small rock, the force gets larger or smaller depending on the mass of that one object. The force of gravity, Newton theorized, is also proportional to the mass of the second object. In this case, could be the Earth. If you take the apple to the moon has a smaller mass than the Earth, then the force of gravity on that apple is even smaller. It is less than what's on the Earth. If you take it to something larger like Jupiter, then the force of gravity of the apple on Jupiter is greater because the mass of this object affects the force also. And Newton also realized that the force of gravity is proportional to the inverse square of the distance, which means you get the larger the further apart these objects are, the smaller the force. You double the distance, the force changes by 1/4. You half the distance, the force changes by a factor of 4. It gets larger. Larger the distance, smaller the force, smaller the distance, larger the force. We write all of these proportionalities into one proportionality. Remember, they have to be proportionalities. They can't be equal because force does not equal mass. So we call them proportionalities. So this gravitational force is proportional to the mass of one object, proportional to the mass of the other object, and inversely proportional to the square of the distance. In order to change a proportionality into an equality, we must multiply it by some constant. And this constant was experimentally determined, but Newton did not know what that constant was, but he knew there had to be a constant in there. The way we write this now into an equality is the force of gravity is equal to what we call the gravitational constant G times the mass of one object times the mass of the other object divided by the distance between them squared. Now this G, say capital G, it's called the gravitational constant. Now Newton didn't know what this gravitational constant was. It actually took almost 100 years after Newton discovered the law of universal gravitation to be able to experimentally determine that constant. Remember, this constant had to be experimentally determined. And it was experimentally determined by a scientist by the name of Henry Cavendish. And he discovered this, experimentally determined this, in the late 1700s, about 1797, 1798. Remember, Newton lived from about 1642, 1717, 27. So he was not alive when Cavendish discovered the law of universal gravitation. This equation is Newton's law of universal gravitation. You need to know this equation. Now, let's see how this works. We're going to do some example problems using this law of universal gravitation. I'll explain some more specifics as we go through some of these example problems. Let's look at the first one. This is the value of G that was experimentally determined by Henry Cavendish, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. You need to know this number or have it on your index card, either one, or both. The first one, what's the gravitational attraction force between the Earth and the Sun? So we're going to draw the Sun. This is the Sun, and the Earth is some distance away. This is the Earth. The things that we know. Now, you should have this planetary data sheet. This tells you information about the Sun and all the planets that orbit the Sun. This is the radius of the planet, in other words, how large the planet is. This is the mass of the planet, This is the distance the object is from the sun. Notice that's not there because the distance the sun is from the sun is 0. So these are the distances all the planets are from the sun. So you need this data table in order to have the information to solve some of these problems. So the two things that we have are the sun and the earth. We want to know the gravitational force. In order to do that, we need to know the mass of each object. We need to know the mass of the earth. Look on this planetary data table. The mass of the earth is 5.98 times 10 to the 24th kilograms. The mass of the sun, 1.99 times 10 to the 30th kilograms. Now, we also need to know the distance the earth is from the sun, called the orbital radius of the earth. Distances are always measured from the center of one object to the center of the other object, not from surface to surface, but from the center to the center. So from the center of this object to the center of this object, from the center of the sun to the center of the earth, that is the distance the earth is from the sun. We call that the orbital radius of the earth. That orbital radius of the earth is the distance the earth is from the sun, which is 1.50 times 10 to the 11th meters. We've used that before. 50 times 10 to the 11th meters. We want to know this force of gravity. This force of gravity is related to the equation G times the mass of the earth times the mass of the sun over the orbital radius of the earth squared. Now, in the generic equation, we have m1, m2, but if we know the substances, the particles that are involved, we put the subscripts related to those particles, mass of earth, mass of sun. Figure this force of gravity, G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the earth, 5.98 times 10 to the 24th kilograms. Use parentheses, they are your friends. Mass of the sun, 1.99 times 10 to the 30th kilograms, divided by the orbital radius of the earth, which is the distance from the center of the sun to the center of the earth, and that is 1.50 times 10 to the 11th meters squared. Put all that in parentheses. Now, when we put this in your calculator, this number is actually in the numerator. I know it's kind of written off to the side, but that's it's still in the numerator. So basically, this number times this number times this number divided by this square. We put that in your calculator. I'll show you how this works a little bit. Let's see if we can do it this way. Clear everything out here. We can put 6.67 times 10 to the minus 11. Make sure you use scientific notation. You can see that a little better. And then times 5.98 times 10 to the 24th times 1.99 times 10 to the 30th divided by 1.50 times 10 to the 11th squared. Then we press enter. We should get 3.53 times 10 to the 22nd newtons. So the force of gravity is 3.53 times 10 to the 22nd newtons. I'll just keep going. Let's go to number 2. What is the gravitational attraction between two 1 kilogram masses that are 10 centimeters apart? We can actually measure 10 centimeters. You don't have to measure it exactly. I'm going to measure it here. So I have one mass about there and one mass about there. Two 1 kilogram masses. Call this one mass 1 is 1 kilogram. This is mass 2. It is also 1 kilogram. So that you had two 1 kilogram masses sitting in front of you on the table. What is the gravitational attraction force between those masses? And so the distance between them, from the center of this mass to the center of this mass, call that R, is 10.0 centimeters. Notice this is centimeters, and we're dealing with newtons. We want to determine the force of gravity. That's in newtons. Newtons is a kilogram meter per second squared, so this has to be written in terms of meters. So we're going to take 10.0 centimeters and convert it to meters. 1 meter over 100 centimeters. That's going to be 0.100 meters. We have to use that for the distance. So then the equation, this force of gravity, is equal to G times mass of one object, mass of two objects, mass 1, mass 2, over the distance between them squared. We have 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times 1.00 kilograms times 1.00 kilograms divided by the distance, 0.1 0.00 meters squared. That's a 0.1 point. All right. We do that calculation. See if you can put that in your calculator correctly. You get the same answer that I have. It should be 6.67 times 10 to the minus 9 newtons. Notice how small this is. This is extremely small. We can't even notice it. It takes very extremely sensitive equipment to even measure that amount of force between two 1 kilogram masses. So we really don't even notice that force. That's because gravitational force is a very, very weak force. We have to have something the size of the Earth or the Moon to have any significant gravitational pull on something. Now, this is the gravitational force between these two objects. What does that mean? That means this mass 1 is applying a force on mass 2 equal to this, 6.67 times 10 to the minus 9 newtons. According to Newton's third law, for every force there's equal and opposite reaction force, so the force on this one due to this mass, the force on mass 1 due to mass 2 is this exactly the same. Equals 6.67 times 10 to the minus 9 newtons. So when we say what's the force between them, it's this force. That's the force on this object, and it's the force on this object. They apply that force on each other. All right, let's go to number 3. What if we have two people? Susie has a mass of 77 kilograms, and Arden has a mass of 90 kilograms. Two people standing appropriately social distance apart, which is about 2 meters. What is the force of gravity between those two people? Draw a diagram. This is Susie, so the mass of Susie is 77 kilograms. This is Arden. Mass of Arden is 90.0 kilograms. And the distance between their centers, call that R, is 2 meters. We want to determine the force of gravity between those two people. Any two people anywhere in the universe, on the Earth, anywhere in the universe, have a gravitational pull on each other. According to this equation, force of gravity equals G. This is the mass of Susie times the mass of Arden over the distance between them squared. This would be force of gravity equals 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Mass of Susie, 77 kilograms times the mass of Arden, 90 kilograms divided by the distance between them, 2 meters. Don't forget to square that distance. Get that force of gravity. See if you can put this in your calculators correctly. We should get a force of 1.15 times 10 to the minus 7 newtons. Notice that again is an extremely small force. It's barely noticeable. In fact, we don't have instruments in our classroom even come close to measuring that force. It's extremely small. That's why you don't feel that gravitational force between objects when you walk by them. It's just way too small to be able to feel that minute of a force. One more problem. What is the gravitational attraction between the Earth and a 90 kilogram person on the surface of the Earth? So now we'll draw a diagram. While you draw a diagram, this is the Earth. This is a person on the surface of the Earth, not drawing the scale. So this is what we have. We know the mass of the Earth. We look it up on our table. We've already had this in a previous problem, 5.98 times 10 to the 24th kilograms. Sorry, we want to know the force of gravity between these two objects. The mass of the person is 90 kilograms. The distance between them, this is the distance the person is away from the Earth, is from the center of the Earth to the surface of the Earth where the person is standing. So that's basically the radius of the Earth. So we look up on our information sheet, the size, the radius of the Earth, and the Earth is 6.38 times 10 to the 6 meters. So this is 6.38 times 10 to the 6 meters. We were able to look that up. And now we use this force of gravity. Force of gravity is equal to G times the mass of the Earth times the mass of the person divided by the orbital, or the distance the person is from the center of the Earth squared. So this force of gravity, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Mass of the Earth, 5.98 times 10 to the 24th kilograms. Mass of the person, 90 kilograms divided by the distance between them, which is the radius of the Earth, 6.38 times 10 to the 6 meters. Don't forget to square that. Do this on your calculator. Pause the video, see if you get the same answer that I got. This force of gravity, capital G, should be 882 newtons. Now, we've been using another way all year long to determine the force of gravity. Remember, force of gravity is how much somebody weighs. And if somebody's on the surface of the earth, we've been using the equation to determine the weight of that person or the weight of an object that's on the surface of the earth. That equation, this force of gravity, this is a lowercase g equals mg. Notice in this equation we're using the acceleration, not just masses. So then, if Newton's law of universal gravitation is correct, we should get the same answer using this equation as we do this equation. Let's see if we do. Force of gravity, the mass of the person is 90 kilograms, times the acceleration of gravity, 9.80 meters per second squared. If both these equations are valid, we should get the same answer. Do that calculation, and if we take 90 times 9.8, we get 882 newtons. They are the same. So then you ask, why don't we just use this equation all the time? Because this equation is relative to somebody that's on the surface of the earth, because we know the acceleration of gravity on the earth is 9.80 meters per second squared. There are many times when the acceleration of gravity on an object or a person is not 9.80 meters per second squared. For example, if this person would be like an astronaut above the surface of the earth. Notice now the distance that person is from the center of the earth has increased, which means their force of gravity is changing. If it has a smaller force for the way that it gets, then this acceleration is going to be smaller. And we're going to eventually learn how to figure out the weight of a person off the surface of the earth or the weight of a person anywhere in the universe. But at least we know that the force of gravity based on the masses is the same as the force of gravity based on the acceleration of gravity. This is called inertial mass in this equation, and this is the mass in the gravitational mass in this equation. We're going to stop here today. You now have a worksheet that you can do. Make sure you download that worksheet. You can put it in Notability or you can print it out. You're not going to turn it in, but we are going to check it. And we're going to have a quiz over Newton's law of universal gravitation. That's it.